So the topic tonight is entitled Discovering the Darkness, Dark Matter, and Dark Energy. And I subtitle it as an overly simplified tale of how we came to know that most of the universe is dark. So I'm going to start you all off with a mini course or micro course in general relativity. And once we finish with this micro course, you'll all be beginner experts, junior Einsteins in general relativity. So you probably heard of Albert Einstein before. You may even have heard of general relativity before. General relativity is Albert Einstein's greatest achievement. He came up with a theory that describes gravity in our universe, and it is just every way we figured out how to test it, it has met the test. So it is an equation which you see in the central white box in the picture. And the important parts of that equation is on the far right, the big capital letter T represents all the stuff in the universe, all the energy, all the matter, anything that like light, anything that you might point to would be that. And then on the far left, the big G is what space, how space is curved and bent in response to that stuff that is the T over on the other far side. And out of this equation comes all kinds of spectacular things, like the prediction the Big Bang happened, the prediction that light will be bent around stars, which is called gravitational lensing, the prediction of gravity waves, if you've heard of LIGO, the observatory. All this stuff comes out of this equation. And when Einstein first put this equation together, he realized that the stuff in the universe would pull everything together because gravity causes this kind of attraction thing, and everything must be moving towards everything else, must be kind of coalescing and condensing together. But being the good scientist he is, he went to the astronomers and said, what do you see? When you look at the galaxies, do they all look like they're pulling together, or are we all moving together to some kind of common place, collecting because gravity is pulling us all together? And the astronomers at the time, and this would be in the early 1900s, didn't have any data that said any of the galaxies were moving. In fact, they basically told Einstein that the universe, as far as they could tell at the time with the instruments and techniques they had, was static. So it was called the static universe. Everything kind of just stayed where it was in one place. Well, that presented a little problem for Einstein because he knew gravity would pull everything together, and yet the astronomers who were measuring the universe are telling him, to their best of their knowledge, it's all sitting still. So it was possible in the mathematics, without violating the basic principles that this general relativity was based on, to add a constant number, which is shown at that yellow arrow in the middle of the equation there, which would just act to repel gravity, a kind of anti-gravity thing. He didn't know what it was, but he knew that if the astronomers were right, he needed something to balance the pull of gravity. So he put this number, called lambda, into his equation to counteract the effect of the stuff in the big T. So that is kind of where it first started off. So now that's it. That's the little micro course on general relativity. There's the big G, which is the curvature of space. There's the big T, which is all the stuff in the universe. And those two want to pull everything together. And there's a big kind of pyramidal lambda Greek letter in there that's something that Einstein didn't know what it was, but he knew something had to be in there to stop that from moving, to replicate what the astronomers were telling him they could see. And so he put that in his equation. So that's it. That's where it started. And that number, lambda, is called now the cosmological constant. They didn't know what it was. It was a constant, it was a number, a fixed number of some value. And Einstein didn't know exactly what that number was, but he knew there's something had to sit in there. And the math was okay with there being a number there. Okay, so next slide. So that's your micro course in general relativity. It's some fancy equation. Now, here's how the talk is going to unfold that I'm going to give you. It really lays out in 3 chapters. In chapter 1, there's a group of people, and too many to name, but one of those people was Hubble. And they were doing what I would call watching the universe move. And so, so this is now after Einstein had put out his equation, and these are just people who are astronomers measuring the universe. So they're out actually determining how is the universe moving. They have new tools that earlier astronomers didn't have. That give them improved ability to measure the movement of the universe. And out of this group, they eventually discovered that the universe was expanding. And then later on, they discovered that it was accelerating. And that allowed them, using Einstein's general theory of relativity equation, yes, that equation, to calculate how much dark energy there is in the universe. I'm going to walk you through in more detail and explain that to you. And then if you go to the middle, chapter 2, there's a different group of people. Again, many famous astronomers, one of which was Vera Rubin. And they were focused on doing things that I would call weighing the universe. They were weighing how much matter and stuff was inside galaxies. They were weighing how much matter and things were inside clusters of galaxies. And they were able to determine, and I'll go through and explain how they got to that determination, by measuring that there was apparently a whole lot of dark matter, that stuff they could not see that was making gravity that they couldn't account for. And so that's the second group. Then in the third chapter, I'm going to tell you, and these are really short chapters, they're just a couple slides each. Chapter 3 is a totally different group, working all off to the side. So we have these first 2 groups that are empiricists. They are people who measure stuff. And then this third group, they are modelers. They do take things like Einstein's equation of general relativity, and they add many other sophisticated models to them. And they were able to do things like use general relativity to predict the Big Bang. They were able to model what they expect the cosmic microwave background radiation to look like and features in the current universe. And from that modeling, which I'm going to walk you through, they were able to determine also themselves how much of the cosmological constant or dark energy had to be there to match their models, and how much dark matter had to be there to match their models. Now, the modeling people, being a different group, they have different names for everything. They call their stuff lambda, which is the same thing as dark energy, and CDM, which stands for cold dark matter, which refers to dark matter. So, but everybody likes to name things differently. Okay, so that's the kind of little tale, the Reader's Digest version. So if you jump to the next slide, I'll jump into chapter 1. Okay, Hubble. So if you remember back to the micro course on general relativity, they told Einstein that the universe wasn't expanding, it wasn't contracting, it was static. And so he added, as you can see, the equations near the bottom, the left one, they added that kind of pyramid-shaped lambda thing in there to balance gravity. But when Hubble measured the galaxies with new instruments that other people had never used and combined it with data that other people had never used, or never put together, he was able to determine that the universe was actually expanding. It turned out that if the universe is expanding, or contracting for that matter, you don't need that lambda, that pyramid-shaped cosmological constant thing in the equations of general relativity at all. And so Einstein actually rewrote that equation again to the equation on the right, where they keep the big G, they keep the big T, but the lambda thing went away. And Einstein, when he did that, he then started to refer to the fact that he had previously put that cosmological constant, that lambda, into his equation as the greatest blunder in his life, or at least that's the story that goes. There's no really good written documentation, but that was an interesting comment that they made. So we've moved now from a static universe where nothing was moving to getting more detailed measurements, and discovered that the universe actually was moving and it was expanding. So if you'll go to the next slide. So further measurements, as they tried to get more and more detailed measurements of how quickly it's expanding, and if you measure how far it's expanding close to you versus far away from you, because light takes time to travel, when you measure the expansion close to you, you're measuring a recent expansion rate, and when you measure far away from you, you're measuring the expansion rate in the past. They were able to plot up how it's expanding over time. And what you would expect was, even if it's expanding, it would be slowing down because gravity would be pulling it back. It's kind of like when you throw an apple up, it may be, after it leaves your hand, it will continue to go up for a little while, but it'll slow down, and eventually stop and turn around and come back. But what they discovered was, long in the past, it was expanding and it was slowing down a little bit, and then instead of stopping, it started speeding up. And today, it's actually speeding up. It's accelerating. So it turns out, though, that lambda, that cosmological constant that Einstein originally put in to hold the galaxies from collapsing static and to hold the universe static, was exactly perfectly capable of also doing this kind of expansion thing. But you just have to start off as it just has to be a small value. So at the beginning, when the universe is slowing down, this lambda thing can't speed it up much because it's too small. And only after it's slowed down long enough is it such that the lambda actually starts speeding it up again. And they could use this data, and by the way, two groups got the Nobel Prize for it. The one group was the high Z, which means great distance, supernova search team, and the other one, the Supernova Cosmological Project. Both of them were able to determine that the universe was slowing down and then began speeding up, and that exactly the shape of the curve of slowing down and then speeding up, which is shown on the left here, would be perfectly explained by the equations of general relativity if it had that lambda back in the equation. So, and they can now use this shape to determine how big that lambda is. It turns out that that lambda, which is an amount of energy, is an incredibly small amount of energy. And it's an amount of energy in every volume of space, every cubic meter or every square kilometer. It's an inherent part of space. And so they use this data to determine how big that amount of energy is. And that amount of energy is, and you can written it out in the bottom there, it's 100th of a millionth of an erg per cubic centimeter. So now for those of you who don't know what those units are, a cubic centimeter is about the size of a sugar cube. So I'm going to talk about amount of energy in a sugar cube. And it's 100th of a millionth of an erg. Now, how big is an erg? Well, several of you probably noticed there's a little picture of a fly there. So when a fly does a push-up from the table to full standing up on its legs, that's about 1 erg's worth of energy. So it's 1,000th of a millionth of a fly push-up per sugar cube of volume in space. So an incredibly tiny amount of energy. So now this group is able to determine by watching how, this is how this first group, by watching how the universe moves, was able to measure how much dark energy is in the universe. And that's a very small number. But later, you'll find out that that's a huge effect because it was, there's a lot of sugar cubes in a volume to fill up the universe, just a crazy huge amount. So it turns out that dark energy will actually be the largest contribution of what's in the universe, because it's so, even though there's so little of it in a given little volume, there's so much of that volume. So next slide. Okay, so that's how the people watching the universe moved, or were able to measure dark energy. So now I'm going to talk about chapter 2, how the people in the group that were watching or were weighing the universe were able to measure how much mass was that they can see, and they know that there's a whole lot more than what they can see. So Vera Rubin, what she's famous for is measuring the speed of stars going around a galaxy. Many of you know that these spiral galaxies spin. And the picture with the overlay graph is actually from M33, a very prominent member of our local cluster of galaxies. And she measured the rates at which stars go around near the core versus further out. And you can see in this graph, the horizontal axis is how many light years out from the core she's going to measure, and the vertical axis is measuring how fast the stars are going around. And there are two curves on there. One is a lower, just gray dashed line curve, and based on what she can see in stars and gas in this galaxy, you can predict that that's what the star's speed should be going around at. And it's related to how much mass is inside the orbit of the star around the center of the galaxy and how far out you are from the center of the galaxy. And so what you should expect to see is that it's slow right at the center, then it builds up at some point kind of near the edge of the core, and then as you go out into the arms, it slows down and drops off. That's what you would expect to see. The upper curve on that same graph is kind of a combined set of two sets of data, where the yellow dots are from looking at stars themselves, which are very bright, and there are many stars to look at in most of the galaxy. But once you get far enough out in the galaxy, it's easier to measure the speed of gas clouds moving around. So the blue dots are actually for gas clouds moving around, hydrogen gas clouds moving around further out in the galaxy. And what you see is something very different. You see that the speed is lowest at the center, but as you keep going out, it just keeps rising, which means that there is ever more and more amount of mass inside that orbit that's going up much faster than what you can see with the stars. And so she could report that there's a dramatically larger amount of matter than what she can see in stars and gas clouds in the galaxy, and they don't know what that was. And they thought for a long time, is this black holes, is this planets, what is this stuff? And they just did not know. But now they have this vexing problem that they're seeing a lot of it, but it's dark. They don't see it. They don't see it in microwaves like the hydrogen clouds are, or invisible like the stars are. But there's a whole lot of it, and it way outweighs the stuff they can see. So next slide, please. So so that last thing was one of the first pieces. Here's another very interesting piece of data. Is two pictures, and I'm going to start with the picture on the left, the one that's kind of mostly red. So this is what's called the bullet cluster. So, and all those little dots you see in there, which you might think of as stars, are almost entirely galaxies. And they're actually clusters of galaxies. And so there's a solid red circle on the left, which is a group of galaxies inside that circle called the big subcluster. And that group is moving to the left. And then over on the right-hand side of that same picture, to the right of the red middle, there's another smaller circle called the small subcluster, but that cluster is moving to the right. And it turns out that the big subcluster and the small subcluster actually passed right through each other in the distant past. And what you see as red, big fuzzy red stuff in the middle dashed circular area is actually it's an X-ray image from the Chandra X-ray telescope of gas clouds that have been excited, which were with the small subcluster and the big subcluster when they pass through each other, but galaxy clusters and galaxies even will pass right through each other and never hit stars. It turns out that although they look really solid, they're almost entirely empty space. But when you pass a galaxy through another galaxy or a cluster through another cluster, what does hit each other are these enormous gas clouds that are vastly bigger than stars. They crash head on, they get enormously heated up, and they glow in the X-rays, and they fall behind. So when this big subcluster and the small subcluster crashed through each other in the middle of that picture, they left behind their gas clouds. And by looking at the stars in that picture and looking at the gas clouds in that picture, they can tell that the vast majority of the matter is in the gas clouds. It's like 80% of the matter between the gas and the stars is in the gas. Very little of the stuff, and that's true in our galaxy too. There's a large fraction of the mass is in the gas clouds that haven't condensed into anything. So that's what's going on in that left visible picture. Now, general relativity told us and predicted that light, when it passes by a heavy, massive object, will get bent. And so that's called gravitational lensing. And these clusters have galaxies behind them. The big subcluster and the small subcluster have galaxies behind them. And the light of the galaxies behind them gets bent as it goes by them on its way to us. And we can see that in the pictures. And by creating a model of how it's bent, we can predict where the mass has to be to bend the light the way that it has to be bent to show up the way it shows up with us. And now what you would expect is that it would be bent mostly where the mass is. So since I told you in the red picture, most of the mass is with the red gas clouds that fell behind when they passed through, when the subclusters pass through each other, you'd expect it to the predicted bending to look like it's bent around that central red gas cloud. Turns out it's not. It's bent around the subclusters themselves. And that means that most of the mass isn't from the gas or from the stars, it's from dark matter. So there's a whole bunch of dark matter that's bending light out there with galactic lensing, and it's dramatically more than the stars or the gas clouds. In fact, 80% of the mass is in this dark matter stuff again, not in the gas clouds, not in the stars. That's how much you need in dark matter to bend the light the way they're seeing it bent with these galactic clusters. So they use these two things now, the speeds of the galaxies, the the clusters, also the cluster speeds rotating around each other, the members within a cluster, how it's bending the light from behind the clusters to measure how much dark matter, and they come up with this amount that this cold dark matter is about 80% of the matter in the universe. So next chart. So kind of just summing up again. So what we have is the group that was watching the expansion of the universe knew, using general relativity, that there had to be dark energy to explain the acceleration and the slowing and then the acceleration of galaxies over time. And then we have the separate measurement group who also used general relativity to measure the mass of a galaxy and found that most of it couldn't be in the stars and the gas, or I should say, and then when they did similar things for weighing clusters of stars, they found that you needed a whole lot of dark matter to account for the bending of light that general relativity says you would. And by the way, general relativity has been validated in how it bends light. That was actually one of the very first measurements they did on it. So what you got is these two empirical groups that says, there is a cosmological constant and I can measure how big it is. And this other, and that's dark energy. And then there's this other group that says, there's all this stuff that looks like it's tugging on things, tugging on stars and galaxy, tugging on light going by clusters of stars. And it doesn't show up. It's not in the clouds. It's not in the stars. It's matter-ish, but it's dark. So now I have two empirical measurements of two unknown things. And now along comes group number 3. Again, many people, one of the more famous people in the next chart, if you'll give me that, is George Lemaitre, a famous astronomer and Catholic priest, an interesting set of vocations. And so he first started working with the general relativity equations, and as a model. So he's not out measuring stuff, he is just modeling. So he takes just general relativity and he winds it backwards in time, and he says, hey, it's all going to crash back together and make this enormously hot, dense state early back in time. And from that would come things like the prediction of, which we call the Big Bang, which was actually a term of derision. When they originally proposed this, someone who thought that it was ridiculous that it would happen would say, you're like saying that this is going to start in some big bang. And it was meant as an insult when it was originally brought up, but people, the name stuck, and so now we call it the Big Bang. So he originally got people kind of doing the early modeling with just general relativity, and then the many other people in the group start adding many other models. So but they're going to use the cosmic microwave background radiation and models to try to predict what from the CMB, what the universe should look like now. And why would they do that? Because it tells you that their models are right, because they know what it looks like now. So if you'll give me my next chart. Now, this one is complicated. Okay, so everybody has their own language for everything. So there is this complicated model called the BAO model, which stands for Baryon Acoustic Oscillation. So I'll pause a moment. So many of these people who are involved in the modeling effort are also involved in atom smashers and particle physics. So one of their terms that they use to refer to for protons and neutrons is called baryons. So you can just think of it as the stuff that our atoms are made out of. That's what a baryon is. The acoustic is, early on, just before the cosmic microwave background is released into the universe, um, the matter was close enough that you would get ripples and waves going through it, and they resemble actually sound waves going through air. And so they have a lot in common with acoustics and oscillation. So the O. So quantum mechanics requires, again, this particle physics thing, requires that the matter in the universe not be uniformly spread, that there be these minor variations um, due to the uncertainty principle in different locations. And so some places you'll have a little bit more of stuff, and some places you'll have a little bit less. And what will happen now is in the places you have a little bit more, you'll have stronger gravity there, and things will start fall around it. It'll start falling into it. And then later, as it starts to condense around the central area, instead of just continuing to collect, the photons that are present at this time actually kind of act as a spring to push it back out. And so it actually goes in and out around these kind of central areas of greater mass in an oscillation, kind of like a pendulum swings back and forth, or a mass in a spring oscillating up and down. And so you can build a model of that, and people have, called the BAO model, and you put into that some amount of baryons, and you put in some amount of photons, and you put in some amount of dark matter, because you've got the empiricists over there telling you there are dark matter and there's photons, like and real solid matter. I can see baryons. So it's like they know they have to put those in. And you might say, well, what about the dark energy? Well, at this time, the universe is much smaller. Before the cosmic microwave background is released, it's much smaller. So that means the number of cubic sugar cubes of dark energy in that smaller universe is much less. So they actually don't put dark energy into these models because there isn't enough of it, because the volume of space is so much less. There's not enough to do anything. So these are models where you can play with it. You can add more baryons and see what happens. You can add more photons or less photons, or you can add dark matter, and you can have knobs and you can turn it up and down. And what you get is that as you go across the top there, you take those inputs and you run it through your model, and you get certain shapes that'll come out in the cosmic microwave background radiation. And you can add more photons and get slightly different shapes, or add more baryons and get slightly different shapes, or take out some dark matter and get different shapes. And so what they do now that they have this model and these knobs that they can put in or take out real regular matter and photons and dark matter, is they actually turn these knobs to match what is actually measured for the cosmic microwave background radiation. They ask themselves, how much baryons versus photons versus dark matter do I need to get my shape to match the shape of the cosmic microwave background radiation? And of course, we've measured the cosmic microwave background radiation in the lower part. You've seen that kind of aqua blue oval of the sky, which is what the Planck satellite has measured for the cosmic microwave background radiation, where the bluer parts are those denser, cooler places where stuff was collapsing into, and the redder parts were less dense, hotter places where matter was flowing out of. And you can characterize the spots in that picture in those graphs on the right, and you get this very interesting shape where it tells you how significant the spot is versus spot size. So the horizontal axis there is spot size, and the height of the peaks is how important the spots are. And so the people above can now turn their knobs, how many baryons, how many photons, how much dark matter gets me the same shape. And out of that, they get the same numbers that the measuring people get for dark matter versus photons versus light matter. They can match the results of the people who are measuring the dark energy, they can match the results of the people who are doing dark matter by not by looking at what they got, but by simply matching what they have to put into their model to get their results to match the cosmic microwave background radiation. So a totally different way, has nothing to do with measuring what is going on for measuring the expansion of the universe, nothing to do with how fast stars are going around or the bending of light from the clusters. It's from the reverse direction. I know the laws of physics, and if I put this much baryon and photons and dark matter in together, the cosmic microwave background radiation will come out like this, and I have to set the knobs of those things to the values that they're actually measuring to get my curves of the CMB to match, the model curves to match the actual measured curves. Totally separate thing. Now, okay, so that's really cool. And then that really makes you feel like, well, you know, that really reinforces what they're doing over on those other two measurements for dark energy and dark matter, because this is nothing to do like that, and I come out with the same results. So if you go on to the next page, then these model people, they have another trick up their sleeve. So on the left, you can see one of those little dark spots, and you see a ring. And that ring you see expands out, and so it is just, as it starts off here in red, it is falling in, and the photons are now pushing out that ring, and that ring is those baryons in the model. And it pushes it out into a ring. And it would normally be oscillating in and out, but they don't play the rest of the video of it going back in. But so that is the baryon acoustic oscillation for one spot. Now, it turns out that when the universe cooled to a certain point, that electrons and the baryons combined to form atoms, then all of a sudden the photons didn't act as a spring. They just flew right by it. And the baryons in that circle, in that ring, froze. They stopped being pushed by the photons. And their model can calculate how big those rings are at the time when the cosmic microwave background radiation got let loose because the universe had cooled enough. And that was the 13.8 billion years ago. And those rings were only 150,000 light years across. Now that's pretty big, but that's pretty far away also. And they know from their models how big those are. So now they can, what that ring is more stuff. It's more atoms. And wherever you have more atoms, you will get more galaxies to form. So it turns out that that ring of baryons turns into a ring of galaxies. And you can see that the galaxies are distributed in the sky in these rings around these central areas. Yes, it's actually a sphere, but when you look at a sphere of increased density through the edge, it looks thicker, and you look straight through the middle, it looks thinner. So when we look from the Earth, we see it as rings. And the ring, and because we knew how wide that ring was at the beginning, now as the universe expands, that ring will expand. And if I measure the distance out to those galaxies in that ring, and I know how far away it is, and I can see how angularly, how big across it is, I can see that ring get stretched out over time. That's an independent measurement for the expansion of space over time. And so the model said, hey, you should be able to go see those rings and measure them. If you measure them at different distances, you will see the size of the rings change. And so the Sloan Digital Sky Survey did just that. They actually went out and started measuring galaxies all at one kind of small range of distances, looking for those rings. and they did it in a kind of statistical way. And so you can see on the right is actually kind of a cartoon at the top of Sloan's work, and at the bottom is their actual data. And they can see that there are a large number, a statistically noticeable number of galaxies that are a ring's distance away from the central area. So that now gives them an independent measurement unrelated to supernova for measuring distance and therefore expansion of the universe. By the way, there's yet another one that's just coming online, another way to measure distance at great distances other than supernova, and which are standard candles, and that is black hole mergers are now going to be used as a standard, what they call siren, not like a police siren, where they are going to use the strength of the gravity wave signals as an independent measurement for distances, and be able to start measuring the distances to things and watch and use it as another way to determine the expansion history of the universe, to determine dark energy. Okay, next slide. Oh, okay, all that stuff. Oh, you must be exhausted. I know I am. So when, we had these three groups. We had one group that was watching how the universe was moving. They were using supernova versus distance to measure the expansion of the universe. And they were able to determine, using their data and general relativity, how much of the universe, or the density of dark energy in the universe, hundredth of a millionth of a fly push-up per sugar cube, and you multiply that up by the volume of the universe, and you find out, you get an enormous number for the amount of dark energy. You find out that the dark energy, that lambda, that kind of pyramid thing, is 70% of everything in the universe. And you take that data from the second group that we're measuring the speed of stars going around galaxies and the gravitational lensing of around galactic clusters, and you can then measure the amount of dark matter, and you find out that's 25% of the matter. And I don't know if you've noticed on the very first slide before I even started, I had a kind of a little colorful, beautiful picture that was kind of modeled purple and red. And that picture is from, go back up and read the credit. That picture is actually the dark sky, or the dark matter map done by the Kilodegree Survey, where they're actually measuring gravitational lensing in every direction to determine how much dark energy is there. So they're now building maps of where this dark energy is. And one of the, the dark matter is. And one of the really interesting things is that the change in perspective we're getting now is that the stuff we see, the hydrogen gas, the stars, the planets, everything that we're thought originally the universe is really kind of like the foam carried along by wherever the cold dark matter goes, and it kind of helps clump up the visible stuff. So between dark energy and dark matter, we're already at 95% of the universe. The only 5% left. Most of that is these hydrogen helium gas clouds that were, kicked out of the bullet cluster and run around in our galaxy. If you look at Orion Nebula, or one of the many gas cloud pictures that we take pictures of, that's like 4% of the universe. The stars less than 1%, and just a tiny dribbling of everything else is everything that makes up all the solid planets and life and all that kind of stuff. So by watching the universe move, by weighing it and modeling it, and finding that these are all consistent with each other, that we know now that the universe is mostly dark, but we have no idea what it is. We don't know what dark energy is. We don't know what dark matter is. We've done some experiments, and so we can say that we know things that it isn't. For example, we know dark matter isn't in black holes. And how do we know that? Or large planets that got kicked out of star formation. So if there was, if the dark matter was black holes, just vast arrays of black holes, we'd be able to look in our galaxy and we would see them pass in front of stars, because when they do, they will bend the light and actually the star gets brighter. And there's actually, they went out and they measured how often those events occurred. They're called microlensing events. And they found that they're nowhere near enough of them to account for dark matter. So, we know, and there are theories of what it might be, a number of particles. They've been looking for various subatomic particles it might be, but they haven't actually found any compelling evidence of it being anything. So with that, if you're giving the next slide, I will take questions. No questions?
So I have a question for you. This is Jeff Stevens. You said that early on in the universe, there wasn't as much dark energy. They didn't have to include in the models because there wasn't enough volume for it. Does that mean the universe has been gaining dark energy as it's grown?
Yeah, exactly right. Their best understanding is that the lambda, the cosmological constant, the dark energy, is an inherent aspect of space. It's not a thing like the baryons or photons that are in space. It's an aspect of space. And so their first thought was that it was being generated directly by the Heisenberg uncertainty principle, saying that particles are jumping in and out of existence just because of the Heisenberg uncertainty principle. But when they actually do the calculation for that, they find that they get an answer that is 120 orders of magnitude above the value I gave you, the measured value. And so they call that the cosmologic catastrophe or something like that. And so they don't know what they don't know what it is. They know how big it is. They know it's there because they can see its effects, but they do not know, and they know that it's inherent to space. And otherwise it would have, it would have been concentrated like the baryons, early in the universe. As you shrink space down, the number of these atoms per cubic meter goes up because you give them less space to be in. But that's not the case with dark energy.
So it doesn't have an energy conservation law. Then it just
that's correct. Energy, the conservation of energy flows from oh my gosh, there's a famous female mathematician who came up with, that Einstein went to actually, to come up with many of the conservation laws. And I'm going to kick myself for not remembering her name. But it requires that, and that all symmetries create a symmetry in space, like translating or changing time, is related to a conservation law. And in our universe, there are actually many examples of the lack of conservation of energy. Like, for example, the cosmic microwave background radiation, those photons were actually at red light colors at like 600 nanometers when they were first emitted. And because of the stretching of the universe, they have been stretched out into the microwave region. Well, so the energy they had as a 600 nanometer photon is much, much less than they have as a microwave photon. That energy is lost because the conservation law is violated when you have space that stretches or contracts. Now, space on the scale of the Earth or our galaxy isn't effectively expanding or contracting. gravity is holding everything together, and you just don't have enough cubic centimeters of dark energy to make any difference over that small scale. You have to get to these enormous scales of billions of light years before you're going to get this kind of stretching where it actually violates the laws of conservation of energy. Notice theorem. She's the one that Einstein went to. Crazy smart female mathematician, and she helped him understand what things would and wouldn't be conserved in general relativity. So she's an absolute just goddess of mathematics.
Steve, I have a question. Is there a concept that Einstein's mass to energy equation applies to dark matter and dark energy?
You mean like E equals mc squared kind of?
Could you say that the E equals mc squared equation pertains to dark masses and dark energy as well as baryonic energy?
Yes. So mass. So there's a great presentation. It have to go all the way through where it just says that mass is an emergent property. So the whole idea that things actually have mass might not be the right way to look at the world. It might be that they have energy, and if you confine energy in the right way, you will get mass. And mass is a characteristic of resisting acceleration kind of thing. In fact, most of the energy in, say, a proton is not in the quarks that are inside, that make up a proton. It's in the binding energy between them. It's actually the energy of the bonds that is, of the gluons being exchanged, that are the majority of the energy that make the mass. So in fact, you can actually make, there's a great PBS spacetime explanation where they go through and how if you had, the standard physics box with massless mirrors on all sides and you put photons in them. So this whole thing has no mass, the photons have mass, and this is an unobtainium mirror box with no mass. But if you now try to accelerate that box, it'll have mass, where mass becomes an emergent property of a collection of massless particles. So they believe that mass and energy, oh, by the way, they know, so the mass and energy of dark matter and dark energy also have the same effect. They show up in the Einstein energy momentum tensor, and they curve space, which is why they were bending light from the galaxies behind the clusters. And they can tell by the total average flatness of space that, which is very flat, that both dark energy and dark matter are having, they're curving, they're acting like mass. But dark energy is really weird because it actually acts as an anti-gravity thing, even though it has mass, but that comes out of the math of special relativity. It's very odd. It's the majority of the energy in the universe, but because of how it's put in there, it turns out it gets credited as a negative pressure term. So it's weird. So, okay, did that answer your question? Okay. Next question I will attempt. So, but yes, on large scales, energy is not conserved. There are a number of things that aren't. Time is local. It's not uniform throughout the galaxy. Time flows at different rates throughout the galaxy, depending on the curvature of space. So all kinds of weird stuff that are non-intuitive because we have evolved in an area where that kind of stuff never happens. It's so, you have to be near a black hole or something like that before, or at these enormous distances. You have to be in things you know, where which are very out of our experience.
Steve, Phil Blanco here. I got a question for you, if you can hear me.
Yes, I can.
It's actually about you. But could you share with us how you got to learn all this stuff? Because it's obvious that you know a lot more and a lot more depth and detail that you're presenting. This was an amazing presentation. I know I was active in the chat. It looked like I wasn't listening. I was listening to every word. And you obviously understand a lot about what is going on, and you're able to distill that and make it accessible as well. So can you share with us how you got to learn this stuff without being a graduate student in cosmology?
No. Yeah. Well, so I do have a bachelor's degree in physics. And I did do my senior work with the 2-time Nobel Prize winner. So it's like I've had some of the very kind of sophisticated math background. I've always been an amateur astronomer. So, and I can highly recommend, if you have not seen them, there's an enormous series on YouTube, all free, called PBS Spacetime. I highly recommend it. They have dozens and dozens of these like 10, 15-minute lessons where they break down a little part of this and they walk you slowly through it. And much of it, it's like I picked up from a number of sources, but part of it I would definitely credit to the PBS Spacetime people. So I would very much encourage you, go to YouTube. It's free. And Matt O'Dowd is their commentator. He is a cosmologist and really a communicator, science communicator, really good, unlike me, at explaining things. And it's his field.
Thank you.
Sure. Any other questions?
A question. What is your favorite list of unsolved problems in physics?
Ooh. Let's see. Well, one of the problems that's I think is really cool is, why is there anything in our galaxy or in our universe? So the particle physicists, when they slam things together, you can make matter out of energy. You can just slam actually very high energy photons together and make 2 electrons. But they always come out in pairs of an electron and an antimatter electron, also called the positron. And so there's a big interest in why early on in the universe, when everything was hot and smashing into each other and everything, they would have expected that there'd be identical numbers of baryons and antibaryons. So if there was a proton, there'd be an antimatter proton. If there was a neutron, it'd be an antimatter neutron, an electron, antimatter electron. And when those particles find each other, they annihilate each other again. And so what you would do, what happens is, as it expands, as the universe expands, those photons that are running around creating these particles, and then the particles killing each other off and creating photons again, those photons get stretched out, that energy gets lost, as the other gentleman noted, from conservation of energy, not conserved, as the expansion went on. At some point, they stopped making particles because those photons lost the energy, that when they hit, not enough energy to make 2 particles. Those particles then can still find each other and do away with each other. And they're, as far as they can tell, there should be equal numbers of matter and antimatter particles of all kinds, and they should wipe each other out, and there should be nothing left but photons in our universe. And so there are theories of how this might not be the case, but at the moment, there's no evidence for how we can get things to last. We know about how many must have been created by how much we see today, we can actually calculate that out. And I think it's like for every billion particles of matter and antimatter, somehow 1,000,000,001, there must have been one extra matter particle created than the reverse, than the antimatters. But we're not sure how that extra one got created, because that's all that's left, is that 1 out of 1,000,000,000. And most of the things that are left over from the Big Bang are photons. They're stretched out into the microwave background radiation. They vastly outnumber all the protons, neutrons, electrons in all the galaxies and all the black holes. So that's probably I think that would be really cool kind of stuff. The whole why is the cosmological constant the value that it is? That's an interesting one by itself. Why is it the logic they laid out for doing the calculations from the uncertainty principle perfectly reasonable, but you get 120 magnitude error, order of magnitude error from what they measure? That's embarrassingly far. So I guess is that an answer to your question? Okay. Other questions?
I have a question,
Sure.
Mr. Hallman. I have heard some opinions saying that there may be no dark matter. Maybe it's just a hypothesis.
Mhm.
Is it arguable, or is it like a topic for discussion to talk if it exists or not, or it's 100% proven that there is a dark matter on this universe?
I would say that the evidence is very strong that there is. So what you're referring to, there's something called MONS, modified Newtonian gravity. So people have said, what if the equation that describes gravity, G m1 m2 over r squared equation, isn't really r squared? It's kind of like r squared. So, but not exactly r squared, because if it's kind of like r squared such that over short distances, meaning our solar system, things like that, distances like that, then it's pretty close to r squared, but you have to get really far away for it to be significantly different than r squared. You have to talk about distances like across the galaxy, or something like that. So there were people that argued that they could modify the equation that Newton had originally come up with for gravity and account for some of the dark matter data that was measured for the stars going around too fast, or the clusters spinning around each other too fast. Now, they don't address the whole microgravity lensing things like I talked about the bullet cluster, but what basically put that group of theories to bed was they actually found some galaxies where the stars are not going around too fast. So the explanation from the dark matter people is no dark matter in that galaxy, so the stars are going to go around exactly as you would have expected them to do. But if your argument is the equation for gravity is wrong, and that it's close at short ranges, but over big distances like galaxies or clusters, it's a different equation, then you can't explain why one galaxy would have stars spinning too fast when a different galaxy and another galaxy not. It should be all the galaxies should spin too fast. In fact, they should spin the same amount too fast, kind of thing. So I think that so far as those proposing modified Newtonian, it's modified Newtonian dynamics, MOND, M-O-N-D, um, those theories are basically not well accepted because of these kinds of arguments that they've actually found galaxies that appear not to have dark matter in them. And because the stars are spinning around at exactly the rates versus distance from the center that you would expect based on just looking at the stars there. So I think the presence of dark matter is reasonably well established as that it exists, as opposed to it's just an error in the calculation of what gravity is. But we don't know what that is. And they're looking for all kinds of things for what it might be.
This means that we can't measure it. We can't get like a very like 100% proof that it exists, but there is many evidences and many observations that leads us to assume that it really exists.
That there's something there. Now, if they find a new particle that they haven't seen before, one that say has no electric charge, so it doesn't interact with photons, it doesn't interact with what is it, strong force, but only interacts with the weak force, then so they have ideas of, by what they see it do, they have ideas of if it was a particle, it would have to have these kind of characteristics. It could have no electric charge, kind of thing. So they know that kind of thing, and people are looking for those kinds of particles, but they haven't seen them yet, and they would be difficult to see because they know they interact with gravity, by gravity, but whether they interact, they have to interact either by the strong force or the weak force, or there's no way to detect them. At the moment, everything, so we detect things going on in the universe by electromagnetic radiation, which is everything from gamma rays, X-rays, visible light, infrared, radio waves. All of those are just varying energies of photons. And then we detect things by particles coming to us. We actually have neutrino detectors, cosmic ray detectors, but they have essentially where particle smacks right into another particle, and it creates things that we can see. There are a number of particles that travel through cloud chambers, and we don't see them until they actually hit something. So, but as far as we know, I mean, the data that exists is consistent with there being something there, that it's not just a variation off the equations of gravity that Newton came up with, but we don't know what it is.
Yeah.
We do know things like it's not a black hole, as I explained earlier. People had said, well, it could just be a whole bunch of little black holes, or it could be a whole bunch of huge little failed stars that are, like giant Jupiters, not quite bright enough to glow in invisible light, but big enough that if you had whole flocks and flocks of them, you could make enough gravity. But it's not those things. We can tell it's not those things.
Yeah. Thank you so much, Mr. Hallman, for the explanation.
Sure. Next question.
There are some questions on the chat.
Oh. Any? Let's see if I can see chat. Run my fingers to the chat section. Oh, hold on. That's not the way to chat. This is it. Participants? Is that where it is? No. Okay. Someone want to read the chat questions to me?
Yeah, sure. It says it's from Maria. It says, what do you think about the Venus news?
Oh, yeah. So I just was watching a show just before I started this evening. So they detected a chemical in the atmosphere of Venus that they have no known inorganic method of it being generated. So they are saying it's a possible signature of life in the atmosphere of Venus, which would be very surprising because Venus is incredibly hot. The surface of Venus, many times the atmospheric pressure of the Earth, plus it's 800 degrees Celsius on the surface, which is would melt lead. So nothing we would recognize as life currently could survive at the surface, but in theory, you can have bacteria living high in the atmosphere of a planet. The Earth has bacteria that live very high up in the atmosphere. So it's possible. This work was actually done by a female astronomer who was preparing to, with the radio telescopes, I believe, was preparing to look for this particular chemical signature, which was phosphine, I think it was, on exoplanets. And they decided before they actually looked at an exoplanet, they would try looking at Venus and other planets here around Earth, or not Earth, on Earth, but in other parts of our solar system. And they spotted a spectral line. So when you have chemicals and they're illuminated with light, they will absorb certain colors, and they will tend to absorb multiple different colors. And apparently this is it had a bright absorption at one specific color, but there's question about whether this is significant or sufficient evidence for that chemical, because they would normally look at multiple different absorption lines to see if that's to identify that chemical specifically. It's moderately good data or evidence, but it's one of two things. Either it's a chemical process that has nothing to do with life that we just aren't aware of yet, that goes on maybe in some odd is driven by some of the peculiar atmospherics and surface rocks and temperature on Venus, and it's just exotic chemistry, or it's an unusual life form that floats in the clouds. So it's probably the former, not the latter, but it's always exciting to think about the possibility for life. The possibility for life on Mars is, been the focus of NASA for quite a while. That's what a lot of the rovers are sent for, looking for signs of life or past life in the rocks of Mars. And there's a whole group that are very interested in looking at some of the moons of Jupiter that have an icy outer core or outer surface, and they believe there are oceans of liquid water below them, where they think life might well exist. So that's my commentary on the Venus. It's early, it's interesting, but don't buy stock in raising Venusian pets yet.
Yeah, it was just a fun topic that came up this week. So
yes, it is.
do you have any idea or have spoken with anyone who is working on finding out if silicone-based life form would exist somewhere that we could observe and what it would be like?
So some people have speculated on that, and that's almost, I don't know that there's been any work other than speculation, and that was almost entirely based on the fact that silicone, I believe, lies in the same column on the periodic table of elements as carbon. And so it has similar ability to form bonds, but at much different energies. So I don't know if it would have to be much hotter or much colder. I can't remember which direction it goes. So no, the last, I mean, you can see such things in Star Trek. Years ago they started saying, hey, rock creatures. So it's cool, it's interesting, and there are people who actually look for life. I think the first thing we'll find, first off, there's no evidence yet of life on another planet. The closest we ever got at one point was looking at Mars fossils. So there have been rocks found in Antarctica that were, yes, it was called the Horta. There are rocks that were found in Antarctica that were believed to have been asteroids or meteors that were knocked off the surface of Mars. And in one sample, they found unusual shapes that one analyst thought resembled fossilized bacteria. So that was kind of the most exciting point. And there was actually a news conference, I think, held by whoever was president at the time to talk about that aspect. Now, without any evidence, such as opinion, I think it's quite possible that it could be microbial life in other places in the solar system. I think that's not at all unreasonable. I would not be surprised if someday, NASA reports back that they found in the salty, briny water of Mars under surface some bacteria that live there or something like, or one of Jupiter's moons. They have a Jupiter, probe, that they proposed to send, where they fly this robot onto the surface of Ganymede, Callisto. It's one of the icy moons of Jupiter. And they have a little heater on the front of it, and they melt their way kilometer down through the ice. And then they float around looking for intelligent life, or any life, really. Not really intelligent life. They probably would just be looking for microbial mats or something like that.
Even if it's just some bacteria, it would be exciting.
Oh yeah, we would learn a great deal about life and the creation of life, and how it could happen, how likely it is to happen, what kind of conditions it could be in. When we do, or if we do ever find life, there'll be big questions going, is that life been seeded from the Earth? Did they seed us? There's a whole theory in cosmology called panspermia, where they talk about how life might have arisen at one or just a few places, but because rocks get periodically blasted off of the surface of planets by mostly large meteors hitting and knocking them off, that they might travel, and that some of these life forms might be robust enough to survive in the vacuum of space and the crazy cold and the cosmic radiation and things like that, and somehow survive not getting burnt up, reaching the surface of another planet to take up residence there. So any other questions? Oh. Last chance.
Last chance. All right.
Okay.
I don't see any takers there, Steve.
I've worn them out, and myself. Okay, well, that's it for today. I want to remind you that we put these on our YouTube website. So